Hi, welcome to Physics 108A. I'll be talking about Chapter 2, Motion in One Dimension. So this lecture is just going to be about the first section. We will be discussing overall all the videos that I will be posting. We'll be talking about how we describe motion, both using motion diagrams and also graphically. We will be primarily discussing uniform motion. We're going to talk about instantaneous velocity and acceleration. We'll discuss motion with constant acceleration, and we'll learn how to solve one-dimensional motion problems. And an application of all of this is the situation involving freefall. So, to begin, how can we describe motion? Well, we can represent position using a horizontal axis. The x-axis is a coordinate axis, as we've discussed in the past. When an object is on the right-hand side of the origin, we say that its x position is positive. And when an object is on the left-hand side of the x-axis of the origin, we say its position is negative. Likewise, with the vertical position, if it is above the origin, then our y position is positive, and if it's below the origin, then our y position is negative. So let's say we have a situation in which a student is walking to class. So here, initial time is equal to 0 minutes. The student is walking along at a constant speed, and she spends 3 minutes walking to class, and when she bumps into a friend of hers, they start chatting for a little while, and so they slow down. So for another 1, 2, 3 minutes, she dawdles a little bit and then looks at the time and realizes, oh no, I'm going to be late for class, and she hurries off and speed walks for another 3 minutes until she gets to class. So this is this here is our motion diagram that we've drawn in the past. Now what we could like to do is turn this into a graph. How can we represent this graphically? To do this, we put time on the horizontal axis. We always put time horizontal, almost always. Our vertical axis is our x position. Now don't let this confuse you. The vertical axis is the x position. If this were a ball being thrown up and down, we might put our y position of the ball on the vertical axis, which feels more normal, and we would keep the horizontal axis as time. So I'm going to do my best to refer to these two axes generically as vertical and horizontal to avoid the confusion of the fact that we're putting the x-axis on the vertical axis, okay? So please keep that in mind in the future. Okay, so let's take a look at our motion diagram for these first 3 minutes. The student covers about almost 200 meters, so we can place 3 dots, 1, 2, 3, and she covers the same distance. You see here the same distance in the same amount of time. So here we've reached 3 minutes, and she reaches almost 200 meters. For the next 3 minutes, she goes much slower and barely covers up to 30 to 40 meters. So here we are at about 230 to 40. After another 3 minutes, 4, 5, 6. There we are, 6 minutes. And then for the last 3 minutes, she goes very fast and picks up speed. Okay. On a position versus time graph, a faster speed corresponds to a steeper slope. So here she's walking at a kind of casual pace, and then she bumps into her friend. This is our student. She slows down. We have a shallower slope here. And when she speeds up, the slope also increases. The slope of the graph, remember from algebra, is equal to the rise over the run. Well, the rise is the change in position. What do we call the change in position? Displacement. So the rise is displacement, the run is the time interval about which we are talking. But we've seen this before, delta x over delta t. That, in fact, is our definition of velocity. Therefore, the slope of a position versus time graph is equal to an object's velocity. Okay? It's equal to that object's velocity at that moment in time. We can also call that the instantaneous velocity. Good. All right, let's keep looking at this. We can draw a graph of the velocity as a function of time starting with the position graph. So we have now a motion diagram. That's one way to represent our motion. We have a position versus time graph, and we also have a velocity versus time graph. So let's break it down piece by piece. In the first 3 minutes, the student is walking at a constant pace. She goes about 200 meters in 3 minutes, which works out to be approximately 1 meter per second, if you do the math. She then slows down a little bit for the next 3 minutes, and so you see her velocity is lower. It's a little less than half a meter per second, okay? But still positive. She's still walking toward class. And then finally, when she realizes that she's going to be late, she speeds up and she's maybe jogging a little bit, and here we see a constant speed, right? A constant value for speed for the next 3 minutes. Now notice here we have the velocity on the vertical axis. We have retained time on the horizontal axis. When you're doing these pictorial or these graphical representations of motion, I strongly recommend that you keep the time axis consistent within each problem. So notice we have 0 to 10 minutes, 0 to 10 minutes. They scale very nicely and so on, right? 2 lines up with 2 and so on. So you can see this slope here corresponds to 1 meter per second. This second piece corresponds to a little less than half a meter per second. And the third piece corresponds to about 1.7 or so meters per second. Okay. We can also go backward. Let's say we have a situation where we're given a velocity graph and we want to deduce the position versus time graph. So the velocity versus time graph shows us that we have an object that's going at a speed of 1 meter per second for 15 seconds, and then has a negative speed, -3 meters per second, for the next 5 seconds. So the object moves faster, but what does that negative sign mean? It tells us that we're moving in the opposite direction. Okay, so we start out, let's assume we're starting at the origin. If our velocity is 1 meter per second, that means the slope of this line must also be 1 meter per second. So for 15 seconds, I've covered 15 meters. Okay, there we go. And then for the next 5 seconds, my speed is -3 meters per second. Well, if I'm going -3 meters per second for 5 seconds, how far did I go? Well, we can figure that out. If we write something down, we know the relationship between speed is equal to our change in position or displacement over time. We want to know what the displacement is, so I'm going to multiply both sides by delta t. And we see that we can find the displacement. Oops, that's supposed to be an x. Just undo that. Undo. Delta x is equal to v delta t. Here in the second part, my speed is -3 meters per second. I didn't mean to do that. That's all right. 3 meters per second times my time interval, which is 5 seconds. 5 seconds. Notice that I'm including the units here. The seconds cancel with seconds. 5 times 3 is 15. Don't forget that negative sign. And I've gone 15 meters, which means I must end up back at the origin. And look at this. If I draw this graph, the slope of this is indeed -3 meters per second. Okay, good. Let's do an example. So the graph here gives the position versus time graph for a car. We're asked to first draw the car's velocity versus time graph and then describe the car's motion in words. All right, so the first thing I want to do is draw an axis. So here is a vertical axis. That's going to be my speed, and a horizontal axis. That's going to be my time. And don't forget to label your axes. Always label your axes. Okay, so this is time. This axis is velocity in meters per second. Okay. And now we need tick marks, and I want my horizontal axis tick marks to correspond to the time axis tick marks above. So I'm going to cheat a little bit. Oops, forgot to take that away. I'm just going to draw little lines. Here's 1, 2, 3, 4, 5, and 6. They're more or less lined up. Let's take all of those and just move it down right about there. Okay, that kind of works. And then I'm not going to label them right away because I know that they correspond to 1, 2, 3, 4, 5, 6 seconds. Okay. Velocity, on the other hand, I will need to have their own tick marks. 1, 2, 3, 4, 5, 6, negative 1, negative 2, negative 3, negative 4, negative 5, and so on. These I will label, so that would be, let's call it 2 meters per second. It's a little high, I wanted that one a little lower. Oh, okay, hopefully you get the idea. Here's 4. So I want each of my tick marks, 6. Delete didn't work. Put 6 right here. Okay. And then likewise, negative 2 would be here. So that would be a, where's negative? Negative. Where'd you go? Negative 2. And then here's negative 4, negative 4. Okay, there we go. So this first section, for the first 2 seconds, our object, the car, excuse me, is moving in the negative direction, moving away from the origin in the negative direction. That means the speed must also be negative. What is the speed? Well, we know, nope, I want this one. We know that the speed is equal to the change in position or the displacement in some time interval. So for this first section here, let's call it 1, the change in position is 4 meters, right? So it's actually negative 4, excuse me. Negative 4 meters divided by the time interval, which is 2 seconds. Negative 4 divided by 2 is negative 2. And look how the units work out, negative 2 meters per second. So I can draw a nice line to represent my speed. I think we always have speed as green, right? So negative 2 meters per second would be like this. Okay. For the next portion 2 of my motion, what is the speed here? The speed is, well, it's horizontal, which means my x position is not changing. So my speed must be 0. So my speed is 0, the slope is 0, my speed is 0 for the next 2 seconds. There we go. And for the last part, 3, our speed is equal to the change in, position over the change in time. And that's equal to, so my position now changed final minus initial, right? X final minus X initial over delta T. I don't want to make any mistakes, any more mistakes, I should say. So my final position looks like it's about 6 meters minus my initial position, which is minus 4. So 6 minus negative 4. And my time interval here is from 4 to 6 seconds. So that's 6 seconds minus 4 seconds is 2 seconds. 6 minus negative 4, that's 6 plus 4, that's 10 meters divided by 2 seconds, which is equal to 5 meters per second. So for the final portion of my motion, my car is going 5 meters per second. That's it. So that's what our graph of velocity versus time would look like. Now, part B asks us to describe the car's motion in words. Well, we could say perhaps that my car is parked and there's a big truck in front of us, but lots of space behind us. So I'm going to back out of my spot. So I'm going to go very slowly and carefully, backing out for 2 seconds. And then I'm going to stop as I look for oncoming traffic. And then I'm going to pull forward as I merge into traffic and speed up to whatever speed cars are going next to me. Good. So that concludes the first part of Chapter 2. I hope you enjoyed this video, and maybe the next ones go a little smoother. All right. Thank you.